Hi guys, this will be the last video for chapter number 2 material, and this one deals with household safety. Household safety in electrical circuits. So I will get the PowerPoint up and we'll take a look at this. Okay. So the first thing we have is basically a discussion of um, um, the prongs or the plug that we stick into electrical outlets. And if we think about most of the plugs that we put in, they are of this particular type right here. Okay. So they're a three-prong plug, and probably most of us are familiar with the name for the third prong on there. It's the ground, but we may not realize what exactly it is that does. So let's take a look here. If we don't have that ground, we've just got basically a positive and negative prong. We plug that in. What happens? Current flows right through our circuit. In this particular case, what is this? A dishwasher? No, it's a dryer. Okay. We've got our dryer. Our filament heats up, and everything is great as long as there's no breaks in that circuit. But as soon as there's a break in that circuit, let's say that break touches the metal casing there of our dryer. Our dryer's not working. We don't know why. You know, probably one of the first things we do is we put our hand on the dryer, and then what happens? Well, we've got a pathway for charge to flow through from this electrical outlet all the way through our body to ground. And you can see with the vibrations there, that doesn't look like a very happy fella. Instead, when we've got this three-prong plug, what we have is that third prong basically attaches a wire to the casing of our dryer, our appliance. And now, instead of current running through this person, the current's got a much lower resistance pathway to ground. It's going to go right through the casing through the wire to ground this way. So yeah, there'll probably be a little bit of charge run through the person, but you know the vast majority is going to be running through that third prong to ground. So that's what that is. That's a safety feature. All right. Let's see, what do we have here next? We've got a basic circuit where we've got a number of different appliances plugged in. We've got a toaster, an iron, a microwave, and we're given the power requirements for each one of those things. And then we're asked the question, well, if we plug all these things in, is that going to trip this 20 amp circuit breaker? This 20 amp circuit breaker there, oh dear, I colored with the wrong thing. That 20 amp circuit breaker there is a safety feature. And so if we try to go over 20 amps, that circuit breaker is going to trip, and then it's going to open up and no more current's going to flow. And if we go over 20 amps and we didn't have a circuit breaker, what's going to happen is that wire is going to heat up and now we've got a real fire hazard. So our first question is, will that circuit breaker open? So in order to figure this out, we note here that our maximum current in this circuit is 20 amps. So that means that the maximum power that we can deliver would be, oh, let's see, Imax. Imax. Hey, you guys may not be familiar with these. So back in the day, when we used to be able to go outside, there were these things called IMAXs where you could actually go and watch a movie somewhere other than at home. Okay, probably too soon. So Pmax is equal to Imax times V. All right. Yeah, I can hear you all not laughing at my jokes right now. So 20 amps, and then what's the voltage being delivered? It's 120 volts. And out of this, I get 2,400 watts. 2,400 watts, that's our maximum power that can be delivered to this circuit. And then if we just check out, you know, the power requirements of each one of these individual appliances, we realize that, you know, that's going to be well over 2,400 watts. There's no way this circuit breaker is going to stay closed. Yes, the circuit breaker will open. It opens. So it opens. Okay. The next question we have is, well, what is the equivalent resistance of this circuit? So we need to take a look at the circuit. When we do that, we realize that, oh, I've got each one of these things basically in parallel with each other. So there's 3 resistors in parallel. Use your imagination. And let's see. So I've got my 3 resistors in parallel. What I'd like to be able to do is I'd like to be able to figure out, well, what is R for the individual? So R microwave. What's R for the individual resistors that I have there? Now, if we think about our equation for power, one of our equations for power was V squared over R. And specifically, I'm looking at the power that the microwave requires. And you notice how I've kept the subscript the same on all those. That's very important. Anytime we're doing anything with these power equations or with Ohm's law, we always hold on to the same subscript all throughout our P, our V, and our R, or our V, I, and R. All right, so if I want to figure out the resistance of my microwave, that's going to be V squared microwave over the power requirement for the microwave, if I rearrange that equation. And then if I plug in numbers, this is 120 volts. Let's see, the microwave is 1,250 watts. The resistance of my microwave is going to be 11.52 ohms. All right, so that's the answer for the resistance of my microwave. All right, well, in the same way here, I can figure out the resistance of the toaster. V squared toast. Yeah, toast. It's 120 volts. And the power from my toaster is 1,650 watts. And I get out 8.73 ohms. All right, and the resistance for the iron, V squared iron over power to the iron, 120 volts over 1,090 watts. And that gives me 13.21 ohms. All right. So then I look at these guys, and like I said a minute ago, they're all in parallel. We recall our formula for adding up parallel resistors. 1 over R total is going to be equal to 1 over R iron plus 1 over R microwave plus 1 over R toaster. So 1 over R total is equal to 1 over my iron, which is 13.2, plus 1 over 1 over my microwave, which is 11.5, plus 1 over my toaster, which is 8.7 ohms. And when I do the math there, figure all that out, I get out that my total resistance is 3.6 ohms. Okay, so that's one way to do it. Let me show you all another way that actually is a little bit quicker. Right? My total power requirement, if say I didn't have a fuse and I just let this thing run, my total power would be equal to the sum of these 3 individual power requirements, 1650 plus 1090 plus 1250. All right, when I do the math on that, I get 3990 watts. 3990, okay. And then, let's see, P total is equal to V total squared over R total. So as a result, R total is going to be equal to, let's see, V squared over P. This is 120 squared over 3990. And you guys shouldn't be surprised at all that, well, that I can't apparently write, but that the answer here is 3.6 ohms. All right, there we go. And so, like I said, this is the end of the material for chapter or for test 2, and hope you guys study hard. And if you have any questions, please don't hesitate to ask.